This is another short video where we look at some example problems to help you get the best possible grades for the final exam. And this time, our problems relate to hypothesis testing. As always with these videos, you'll see me using the Wolfram language. Remember, this is not about a computer language though. I'm using it to do my calculations and I'm using it to create the plots so that I can explain the solutions to you. Let's start with question number 1. True or false? A hypothesis is about a sample statistic. And of course you can see my solution there. That is false because an hypothesis is always about a population parameter, not about a sample statistic. Question number 2, define an alpha value. And I've written here, an alpha value is the type 1 error rate, our willingness to commit a type 1 error, which is rejecting the null hypothesis when it is indeed true. Do remember that we can only construct a distribution of possible values under the null hypothesis, as if the null hypothesis is true. All the values that we see on that distribution are possible. We are only selecting those very improbable ones on the lower tail and upper tail, and we are saying that if we find one of the values in those zones, the zones of rejection, we reject the null hypothesis. Great. Define a critical value. My answer here is a critical value is a point on the distribution of the test statistic under the null hypothesis that defines a set of values that call for rejecting the null hypothesis. The set is called the critical or the rejection region. And if we visualize this, it'll make more sense. Now you've seen this before. We concentrated on the most probable values in the middle when we spoke about confidence intervals and the confidence coefficient. This is not what we're doing with an alpha value though. Here we're concentrating on the zones of rejection of a null hypothesis. And so we're thinking of the little blue zones on the lower tail and upper tail here, that there must be some z value beyond which we will reject the null hypothesis. If we find a z value in those blue zones, we will reject that null hypothesis. And here I have chosen an alpha value of 0.05. And guess what? That's going to be a value of negative 1.96 and positive 1.96. That was the same as the confidence coefficient, looking at the center 95%. The confidence level that I chose. Now I'm looking at the zones of rejection though. That if I find a z value in these zones of rejection, so above positive 1.96, below negative 1.96. If I find a z value there for my study, I'm going to reject the null hypothesis. Those were very improbable values to find. And if I find one of those improbable values in those zones, I'm going to reject the null hypothesis. I am saying though that that is my willingness to make an error. We do remember when we discuss the idea of a null hypothesis is that we create this graph as if the null hypothesis is true. If the null hypothesis was really true, all these z values are possible. Theoretically, all the way from negative infinity to positive infinity. It is still possible to find these z values if the null hypothesis is true. We just decide that if we find one of these rarer values, so in these rejection zones, that we will reject the null hypothesis. We will falsely be rejecting that null hypothesis because this graph is generated as if the null hypothesis is true. That's the only thing I can do in hypothesis testing. I can only create this graph under the null hypothesis. So these values in the rejection zones, they are still completely possible if the null hypothesis is true. We've just decided that if it is a value that we find for our one study, if the z value is in these zones of rejection, we are going to reject the null hypothesis. That is our type 1 error rate or our alpha value, our level of significance we also call it. So if I want a 5% level of significance, an alpha value, that would be negative 1.96 on this side, positive 1.96 on this side for a two-sided alternative hypothesis. And that means this little blue area under the curve on the lower tail and this little blue area under the curve on the upper tail, they are 2.5% and 2.5% of the area under the curve respectively. I add them, I get 5%. So I'm looking at the 5% least probable values that z could possibly take if the null hypothesis was true. And we are saying if we find a z value for our one study in these rejection zones, we reject the null hypothesis, but we are accepting here the fact that we are making a mistake in 5% of cases by rejecting that because this graph was generated as if the null hypothesis was indeed true.
true. Great, let's go to question number 4. Calculate the critical values for the standard normal distribution using values of alpha of 0.1, 0.05, and 0.01. Use a two-tailed alternative hypothesis. Now, I've used code here, so let's just run through that. I get for an alpha value of 0.01, I get a value, a critical value of 1.64. For 95%, or an alpha value of 0.05, I get 1.96. And then for an alpha value of 0.01, I get 2.58. Those are my critical values. Remember, these are these red lines, the borders that start these zones of rejection. And if we go to a very small alpha value, we only want a small chance of committing a type 1 error, falsely rejecting the null hypothesis. You can see these little zones are tiny. They're 0.5% on each side. If I use a bigger alpha value, 0.1, I'm willing to make an error 10% of the time. You can see my zones of rejection much bigger. In other words, my critical values, these red lines, the borders here of my rejection zones, they are now much closer to 0. They're at 1.64 and negative 1.64. Now you can use code from Python R. Here's the Wolfram language, but I would advise you just use the spreadsheet that is available in the link in the description down below. So here we have our spreadsheet. Do remember there's a lot of sheets here at the bottom. At the moment we're talking about the Z distribution, so make sure you're using the Z distribution. And for now we're just going to stick to the two-sided. Let's use a alpha value, or a level of significance of 0.05. And once I do that, for two-sided you see my critical values, negative 1.96, positive 1.96. Later on, we will discuss examples where we have one-sided alternative hypothesis. So I'm putting all my eggs in the lower basket, or all my eggs in the upper basket. And if I choose 0.05 now, we see that the critical value on the lower side will be negative 1.6. On the positive side will be 1.6. We'll see examples of those. In most cases though, and typically when I create a final exam for courses on applied biostatistics, I will stick to a two-sided alternative hypothesis. So let's get to an example. Question number 5. If the steps of conducting an hypothesis test are as listed below, consider the following question and answer it accordingly. The waiting time for an appointment at an antenatal care facility for expecting mothers has been recorded since the opening of the facility 11 years ago. The average waiting time in those 11 years is 5.7 days from the time that someone makes the appointment until they can actually come into the clinic, with a standard deviation of 1.5 days. The laws of the state in which the facility resides has changed. Now administrators believe that the waiting time is no longer 5.7 days. They collect data on 74 appointments and find the average waiting time to be 6.1 days. Determine if there's enough evidence at the 5% level of significance to support their assertion. Now, before we go and we dissect our problem, let's look at these steps that I want you to follow. Now, you can write out as many steps as you want. In this instance, I've got a 9-step process because I started step number 0. And so for me, step number 0 is always to summarize the facts that I've been given in the research problem, in this instance question 5, and I just want to write it down symbolically. So I'm going to write mu equals, sigma equals, n equals. I'm going to write all those down just to summarize what I have. Step number 1 would be determine the population parameter. We always have to think about what is under investigation here. It is the population parameter that's under investigation, not the sample statistic. State the null and alternative hypotheses. State the level of significance. State the test to be used. Very important in a course on applied statistics. You have got to decide what statistical test to use. State the test statistic and its distribution under the null hypothesis. State the critical value or values as determined by the level of significance. Calculate the value of the test statistic and measure it against the critical value for the research question, and then write your conclusion with respect to the research question. So let's just take apart our problem here. It says the waiting time for an appointment at an antenatal care facility for expecting mothers has been recorded since the opening of the facility 11 years ago. So I know this mean would represent a population mean. It's all the data that is available. And the average waiting time is 5.7 days. That is going to be my population mean. So in step number 0, I've written that down. Mu equals 5.7. with a standard deviation of 1.5 days. Once again, that will be a population standard deviation. So I write sigma equals 1.5 in step 0. Now the laws of the state in which the facility resides has changed. Administrators believe that the waiting time is no longer 5.7 days. Now think about that. They did not claim that it is now less than 5.7 days or more than 5.7 days. They just said it's different from what the population mean is of 5.7. So I have a two-tailed alternative hypothesis as opposed to a one-tailed alternative hypothesis. So they collect data on 74 appointments. I'm going to write there in a 74, and they see a sample waiting time of 6.1 days. So there's my X bar at 6.1 days. Now determine if there's enough evidence at the 5% level of significance. So I have an alpha value, 0.05. So I like to write these things down in step number 0. Let's go to step number 1. What is the population parameter that we are considering here? The population parameter is mu, the number of days to wait for an appointment. The population mean number of days to wait for an appointment, the population value. Next step, we're going to write the null and alternative hypothesis, and we write that as H sub 0 and H sub 1. So mu is 5.7, the population value is 5.7. Alternative hypothesis, it's not 5.7, it's two-tailed. They did not say they claim it now to be less than or more than. They said it's no longer, it's now different, and that's what we have. Next step, step number 3, state the level of significance. I have it there, alpha equals 0.05. What statistical test am I going to use? Well, for now in the course, we've actually only learned one test, and that is this test, the one sample Z test. I've got one sample of data, 74 data points, just a single sample of 74 data points, values, and I know the population standard deviation, sigma, so I'm going to use a Z test. Now, in step number 5, state the test statistic and its distribution under the null hypothesis. I'm using a Z-test. My statistic that I'm going to test is the Z-statistic. And I know Z is described by, or follows the, that's that little tilde symbol. N stands for the normal distribution on a mean of 0 and a standard deviation or a variance of 1. That's the standard normal distribution under the null hypothesis. If the null hypothesis was true, I would have a Z distribution. And remember here, Z is just a representation of all the possible X bar values if I could do my study many times over. And all those X bars can be converted to a Z value by standardizing each and every one of those infinite number of X bar values by subtracting the population mean and dividing by sigma divided by the square root of n. So now I have to calculate the critical values using a Z distribution and using an alpha value of 0.05. Now here I've used code for that. My lower value, critical value, will be negative 1.96. My upper value will be positive 1.96. So let's go to our spreadsheet and do it there. So here's my critical values calculator. Once again, I am here on the Z distribution sheet at the bottom. I'm using a two-tailed alternative hypothesis and I have an alpha value of 0.05. There's my critical values. Negative 1.96, positive 9.96. Those are my red lines. Beyond that on the lower tail and above that on the upper tail, those are my zones of rejection. If my Z value falls beyond these values, I'm in my zones of rejection and I reject my null hypothesis. But I do remember those are still values possible under the null hypothesis because the Z distribution gives me a distribution of Z values given that the null hypothesis is true. It is possible to find values in the rejection zones even if the null hypothesis is true because that is what that graph represents. We just decide that we are willing to have that error rate, that type 1 error rate, that we reject the null hypothesis given that was in actual fact true, and we are happy with that. We are happy with that 5% value, and we choose that as researchers before the time. So here we go. Let's calculate our Z value from our problem. There we have X bar minus mu divided by sigma divided by square root of n. So X bar was 6.1, mu was 5.7, sigma was 1.5, and we had 74 data points in our data set. Let's calculate the Z value, and I find a Z value of 2.3. Of course, that is more than 1.96, and it is in that zone of rejection. Let's visualize that just to make sure we understand what's going on. There we go. I see my zones of rejection. Now in this instance, I've just made it red instead of what we had before. And so there's negative 1.96, the border there. That's positive 1.96. The two red zones represent 2.5% on the lower side, 2.5% on the upper side. Combined, it is the 5% least probable Z values that I would find given the null hypothesis being true. And I find this little black one there. So I've just drawn a little line there just to make it clear. And so my value was 2.3. My X bar value was 2.3 standard errors away from mu. So it's right out there, and that falls in that zone of rejection. It is beyond the critical values. And so I can now write the following. There is enough evidence in the data at the 5% level of significance to reject the null hypothesis and accept the alternative hypothesis. The population mean is not 5.7 days. And I can actually say it is significantly more than 5.7 days. We found it actually to be more. If we look back at our problem, the mean was 5.7. We now find it to be 6.1, so we can really claim it is significantly more than 5.7. We can now look at the direction. Was it less? Was it more? Well, in actual fact, it turned out to be more, so we think it is significantly more than 5.7. Question number 6. Let's revisit question 5 and determine the 95% confidence interval and interpret that result. Now, we do now know that C is 1.96, our confidence coefficient. We are going to use this equation, X bar plus or minus C times the standard error. And let's plug those in. Remember, you can use the spreadsheet, plug in the values in the spreadsheet, and you will find a lower bound of 5.8, just rounding that a little bit, and an upper value of 6.4. So let's conclude. We are 95% confident that the population mean is 5.8 to 6.4 days. Remember, that's now symmetric around our sample mean. Note that the population mean of 5.7 days from our problem in question number 5 is not in this interval. This is equivalent to rejecting the null hypothesis. Look how these things go hand in hand. Here we rejected the null hypothesis. We found one of these values in the rejection zone. If I convert this 95% most probable values, if I convert that to a lower bound and an upper bound above X bar this time, so I'm taking X bar minus 1.96 times the standard error and 6.1 plus 1.96 times the standard error, I get a lower bound and an upper bound, and look at that. The value under the null hypothesis, mu right up there. Remember, mu was from our problem 5.7. That 5.7 is not in my 95% confidence interval. And so if it is not in that confidence interval, it's the same as rejecting the null hypothesis, which is exactly what we did. These solutions go hand in hand. Great, so let's look at question number 7. Caregivers at a center for drug addiction complain that their workload has increased because they have been seeing an increased number of individuals every day. And of course, the administrators believe that that's not the case. And this is true. We all feel the stress. This is a common thing, but perhaps we're suffering from confirmation bias, that we only remember the days that we worked harder and forget the days that we didn't work so hard. So we've got to test this claim. So to verify the claim by the caregivers, they collect data on 30 random days and note that the average number of persons with addiction-related problems that are attended to every day is 44.1. They compare this to a historic mean of 42 cases per day with a standard deviation of 3.3. Is there enough evidence at the 5% level of significance to support this claim by the caregivers? So let's take this apart by looking at step number 0. They have historical data. It seems like the mean was 42 cases per day, and that's where we have a population mean of 42 with a standard deviation of 3.3. They went out and they collected data on 30 subjects, and that subjects will be 30 days. And so you can see subjects, not always a person, and they see an average of 44.1. Now, what we need to know is to understand, is 44.1 significantly different from 42? And they want the 5% level of significance, so I have an alpha level as well. What is the parameter under investigation? The parameter under investigation is mu equals 42, the average number of cases seen per day. Historically, that's 42. That is our population mean. Null and alternative hypothesis. The null hypothesis is easy. Mu is 42, but now we have to think about the alternative hypothesis. These caregivers, their claim is that they feel they're seeing more people every day. So this is a one-tailed or one-sided alternative hypothesis. They believe that the population mean is more than 42. One-sided, and it's on the upper tail. Alpha is still 0.05. By step number 3, I've got a single sample of 30 data points. I know the population standard deviation. I'm going to use the one sample Z test. The test statistic for this test is the Z statistic, and it is described by the standard normal distribution under the null hypothesis. Now I have to calculate critical values for this, a critical value. I'm just going to use Koji, and I see it's 1.64485. Remember, I can go to my spreadsheet and have a look at this. Let's do that. Here's my spreadsheet. I'm on one-sided greater. They believe the mean is greater than 42. My alpha value is 0.05. Lo and behold, I find a critical value of 1.64. So I know that's the critical value. If my z is below that, I fail to reject. If my z value is more than 1.64, I'm going to reject the null hypothesis. So there we go. Here's our calculation for z. I'm plugging in all those values, x bar minus mu divided by the standard error. I get a z value of 3.5 almost. I'm 3.5 standard errors away from the mean. That is much more than being 1.64 standard errors away from the mean. Let's visualize that just to make sure we understand that. Here is a one-sided alternative hypothesis. My alternative hypothesis was it is now greater than, so I don't split my 5% symmetrically on either side by 2.5% and 2.5%. I put all my eggs in one basket. I put all 5% on this side. And now look what happens. When I had a two-sided alternative hypothesis, my critical value was positive 1.96. Now it is lower, it's at 1.64 because all of the 5% least probable values are now on one side, the upper tail side. So in actual fact, I've made it slightly easier for myself to cross a barrier. Instead of 1.96, my barrier is now only 1.64. So in class, I always warn against one-sided alternative hypotheses. And remember, you can't even see it, but on my screen I can see there's the tiny little black line over there. It was almost 3.5. That 3.5 standard errors away from the mean, that x bar is from mu, that is a lot more than 1.64. I'm in the zone of rejection. I reject my null hypothesis. So we conclude there's enough evidence in the data at the 5% level of significance to reject the null hypothesis and accept the alternative hypothesis. The average number of cases is more than 42 per day. In fact, it is significantly more than 42 per day. These caregivers were right. They are seeing more people on average per day. Revisit question number 7. Calculate and interpret the 95% confidence interval. So we've just rejected the null hypothesis. Do you think that the mean, the population mean mu, will be within the confidence intervals that we calculate? No, it should not be. We've just rejected the null hypothesis. We better find intervals that do not contain the mean value of 42. So there we go. X bar plus or minus c times sigma divided by the square root of n. We know c to be 1.96 for the z distribution and a confidence level of 95%. We've discussed this before. And so there we go. I do 44.1 minus 1.96 and 44.1 plus 1.96. I want to build intervals around the sample mean this time. And if I do those little calculations, I find 42.9 and 45.3. And look at that. 42.0 was what the value was under the null hypothesis, is not within those bounds. And that supports and gives me exactly the same conclusion I did with hypothesis testing, I get with confidence intervals. And that should always be so. So we can say we are 95% confident that the population mean is 42.9 to 45.3 cases per day. Note that the population mean of 42 cases under the null hypothesis per day is not in this interval. This is equivalent to rejecting the null hypothesis. Absolutely beautiful. Let's do one more. The monthly inflation-adjusted donations to a non-profit organization over the last 17 years has been $40,304 per month, with a standard deviation of $5,567 per month. Managers at the non-profit believe that these donations are declining and they should do something about it. They collect data over a period of 30 months and find an average donation of $38,989 per month. Inflation adjusted. Is there enough evidence at the 5% level of significance to support their claim at this time? Step number 0. Let's collect what we have. They have collected data over the last 17 years. That's the data that exists up until then. In other words, that is population mean, 40,304. Population standard deviation, 5,567. The data that they collect now, a sample, gives us a sample mean of 38,989. 30 is the number of data points they have. That's their sample size. And again, look at this. These subjects, the 30 values that they have, it's not human beings. In this instance, it's months. And alpha value is 0.05. The parameter under investigation is mu, the average donations per month. Null and alternative hypothesis. Mu equals 42,304. But look at their claim. They think it's declined. So it's one-sided. The alternative hypothesis is that mu is less than 42,000. My alpha value is still 0.05. I've got a single sample of 30 data points. I know the population standard deviation. I'm going to use a one sample z-test. For that test, my test statistic is my z value, and it follows a standard normal distribution under the null hypothesis. Now we have to calculate a critical value. I'm doing it with code here, and I find negative 1.644. Let's go to the spreadsheet. Remember, link in the description down below. Let's use that rather. There's my spreadsheet. It's one-sided less is what I want. Remember, down here, I'm still on the z sheet. My alpha value is 0.05, and lo and behold, there's my critical value, negative 1.64. So that's exactly the same as I find by using code. There's my z calculation. Let's do that calculation. You can do that. And I find negative 1.29 or negative 1.3. That is not beyond negative 1.64. That is not in the zone of rejection. It is not beyond the critical point. So let's just visualize this to make sure. Now there we go. Once again, standard normal distribution. Remember, all these z values are just how many standard errors away from the mean or possible x bar values would be from mu. If I were to do my study many times over, I find this distribution of some possible sample means under the null hypothesis being true. So these values, even in the rejection zone, they are still possible even under the null hypothesis. But we are just saying we have this line in the sand, the 5% most improbable values on the lower tail. I'm again putting all my eggs in one basket. I'm not dividing it in two. It's not a two-tailed alternative hypothesis. And that means my critical value is right here at negative 1.64 right there. But look what I found. This is what I found. I found negative 1.3. That is not in this zone of rejection. So I'm going to say there is not enough evidence in the data at the 5% level of significance to reject the null hypothesis. The average monthly donation is not less than 40,304 by the sample that I've taken. Question number 10, let's just revisit question number 9, and now I want to calculate the 95% confidence intervals around the sample mean. Now do remember, my sample mean was 38,989. I just want to know what is a lower value and an upper value around that value that would represent being 1.96 standard errors away from the sample mean. And that's exactly what I calculate here. Do remember that there's a spreadsheet for that. And I would suspect that my mean, my population mean, would be within the intervals that I find. Why? Because we failed to reject the null hypothesis under hypothesis testing. So there you go. I found 36,996.9 to 40,981. What was the value under our null hypothesis? Well, it was 40,304, and that is within this interval. I do find the null hypothesis value, the population mean, within my confidence intervals, and hence that would be the same as saying I failed to reject my null hypothesis. That goes with the hypothesis testing. I better come to the same conclusion. Great, you've seen a couple of example problems now. I hope this really helps you to prepare for the final exam.